Question 3 says a trolley of mass 45 kilograms is released at a height of 4.2 meters at the top of a ramp. Calculate its gravitational potential energy at the top of the ramp. So the gravitational potential energy is m times g times h. This is 45 times 9.8 times, it definitely says it's the height of the ramp. So the fact that it's a ramp doesn't matter. If we're picturing it, we're probably picturing something like this, but this is 4.2 meters. We don't know the length of the ramp at the moment. So 4.2. 5 times 9.8 times 4.2 gives us 1,000. So comes out as 1,852.2. We're rounding it again to two significant figures. So 1,900 joules. Describe the energy changes as it rolls this down the ramp. So at the start, we have the gravitational potential energy store. Then on the ramp, we're going to have mechanical work done by gravity. We might say it's done by the weight of the trolley. We'll also have some heating of the wheels and the ramp by friction. So we've got a couple of pathways, and then at the bottom, that will mean we've got lots in the kinetic energy store in the trolley, but we will also probably have some, not very much, but some in the thermal store in the ramp and in the wheels of the trolley as it rolls down. C, for this question, we will assume that all the gravitational potential energy is converted into kinetic energy. What does this imply about the efficiency of the process? Well, what we're effectively saying is that the heating is negligible. So heating is negligible, and therefore there is no thermal energy wasted. And this sort of implies to us that it is 100% efficiency. D, state the size of the kinetic energy of the trolley at the bottom of the ramp. So whenever we see the word state in physics, it's different to seeing the word calculate like we did earlier on. State means you already know the answer. You've written the answer down somewhere already, or the answer is a really obvious number like 0. It's not 0 here. When it gets to the bottom of the ramp, all of the gravitational potential energy it had has been turned so that it's all kinetic energy. So we can state without doing any working out that the energy when it gets to the bottom of the ramp is 1,900 joules. And then part E, calculate the speed of the trolley at the bottom of the ramp. So we know the kinetic energy, we know its mass, and we try to find its speed. So like we did before, we need to use this equation. We need to rearrange it for speed. It's easier to rearrange it for speed squared first. So 2 times the kinetic energy over the mass, and therefore the speed is the square root of 2 times the kinetic energy over the mass. So in this case, that is equal to the square root of 2 times 1,900 divided by the mass of the trolley, which is 45. Don't forget to do the square root again. Use the fraction rather than the divide on your calculator as well. You're less likely to make a mistake. This gives us a speed of 9.189, so 9.2 meters per second.